Okay, grade 12. We are back and we are learning about electric potential and electric potential energy. Just a little bit more in depth than the last time we did it. So let's just jump straight into it. Uh, we've got potential for this to be a pretty quick lesson. So starts off with a really useful formula and a really useful connection between all the formulas. It looks pretty ridiculous, but it's really helpful for when you're actually solving these problems. So we'll start with that. Let me just get myself set up here. There we go. Okay, sweet. I hope that you're all out there enjoying this really nice weather, though, as much as you can. I know that I have been doing some golfing when I can and working in the backyard, going for runs and stuff. Just nice to be able to get outside. So make sure that you're doing that when you can, because I think it really does help. Anyways, let's get right to it. So this following little formula, and it's not just one formula, it's actually a really big series of formulas, helps to describe the way that parallel plates are all related in one relationship that can like always be used together in the following way. And it looks, like I said, quite ridiculous, but it's so extremely useful for when you're doing these problems because you can just refer to this one big series at any point in any question and basically find the information that you need. So work. Work is defined as the change in energy, right? The change in the electric potential energy in this unit. And electric potential energy, we've seen back in the past already, is that electric potential energy is equal to the charge multiplied by the potential difference. So that means, therefore, that work is equal to the change in potential or the potential difference multiplied by the charge. Potential difference, however, is also seen as the electric field multiplied by the displacement. So we can replace that with electric field multiplied by displacement, which then also way, way, way back, we've seen before that the electric field is equal to the force divided by the charge, right? Newtons per coulomb. So we can replace QE with the electrostatic force multiplied by the displacement. So at any given time in any one of these questions, if you get a question, you just have to look, okay, maybe I have potential difference in charge and I have force and I'm trying to find displacement. Well, then I'm just going to set these two equal to each other and solve for displacement, right? Maybe I have, charge and displacement, but I don't have force. I actually only have electric potential energy. Well, then I set these two equal to each other, right? Do you see how this can be useful? You set any two that you need to be equal to each other and you solve. Now, two other ones that we see a little bit less often, but are also technically still in this same vein, are the change in kinetic energy and the change in potential energy. And that just comes from the law of conservation of energy, right? That we've seen way back in the momentum work and energy unit. So you might get a scenario where you've got an electron moving at a certain speed, and now all of a sudden you need to use kinetic energy, right? You might have a problem where the charge is fighting against gravity as well as maybe something that's out of the parallel plate. So you have to use MgH as well. So this is something that I think, yeah, I got to do a better job of remembering exactly what's on your formula sheet. I'm almost certain this is on your formula sheet. So just make sure that when you're looking at this, if it's not, write it on your, do it. Just write it down on your formula sheet. When you're doing these problems, you always have something that you can come back and look at, and it will always help you. Little side note here, what are equipotential lines? So in the area between two parallel plates, so let's draw two parallel plates. Okay, and we'll make the top one positive, make the bottom one negative. Now, in the area between two parallel plates, there's various locations that have the same electric potential. These locations form lines, and they're called equipotential lines. Now, the reason why they have the same electric potential is because they are in the exact same position relative to each of the parallel plates. So let's take a look at where this might end up. If I take a 3 locations right here, one here, and one here, and they all have the same distance from the top plate to them and the bottom plate to them, that means that the electric potential at this part, or at this space between these lines, is going to be equal throughout. It doesn't matter if it's there or there or there or there, it's all going to be equal throughout. And that's because the electric potential, or sorry, the potential difference is equal to 0. So these are called equipotential lines. This right here is an equipotential line. Okay. Now, obviously, if I take a look at, what is this electric field doing? It's all moving downwards like this, right? So at any given point, like there's going to be an equal potential line here and here and here. It just, all it matters is that you have the same distance from each plate to the point. So they're always perpendicular to the field. They're always perpendicular to the field. And to move a charge from one location on an equal potential line to another location on that same line requires no work. There's no change in energy going on. And this is because the potential difference is equal to 0. So if the potential difference is equal to 0, well, that means that, really anything else you can argue is going to be equal to 0 in that case, right? There will be no change in its displacement. There will be no change in its electric potential energy. So no work is required. Okay, work will be equal to 0. Okay, so that's an equal potential line. Now I'm going to post a video underneath on my Google post today as well, talking about something called Millikens Experiment. And I have a video that I like to show about it. It's pretty informative. So I'll post it on there, and you can take a watch after my video, or you can pause and watch it right now. Basically, Millikens' experiment was an experiment done to look at the way that charged objects behave in between parallel plates. Okay, so what he did was he did these like tiny little oil droplets. It's called Millikens' oil experiment sometimes. Tiny, tiny, tiny little oil droplets in which he just induced a small electric charge into them. And then by changing the magnitude of the charge on one of the plates, he could actually adjust the height of those oil droplets at will. He could move them up or move them down, and that really showed that electrostatic force that they're feeling, how it behaves on different charges. So it was really important to be able to get a better understanding of how it all works. So I'll post that video, and you can watch that video when you get a chance. But for right now, let's just do an example having to do with Millikens apparatus. So it's a parallel plate scenario. So a Millikens apparatus is in a vacuum, and he has an aluminum ion. Now, this aluminum ion, if you remember from even in grade 10 science, we learned that it's Al3+. Okay, 3+ means that it has a charge of +3, right? Which means that if I was to quantify its charge in ECs, it would be +3 ECs, right? And that wasn't working very well. Okay. I don't want it in ECs. I want it to be in coulombs. So how do I convert from EC to coulomb? I multiply by what the charge of one electron is, or one proton is, in coulombs. And I hope that we're starting to remember this number maybe by heart now. 1.6 times 10 to the negative 19. So if I do that, I should get 3 times 1.6 is 4.8 times 10 to the negative 19 coulombs. Okay, so that's the charge. Now it's in between the plates. The electric field between the plates is 145,000 volts per meter down. Just so you are aware, volts per meter is actually the same thing as our normal our normal quantification here of electric field, which is newtons per coulomb. I'll show you how. Volts per meter. Well, another thing for volt was joules per coulomb. So it's joules per coulomb per meter. And another thing for joules, as we've seen before, is joules can be quantified as, and I mean, we can even see it up here, force times distance, Newton meters. So you can actually write this out as Newton meters per coulomb per meter. And in that case, we have our meters cancel and we end up with just newtons per coulomb. So there, kind of a little bit of a side I don't know, lesson on how we can always check to make sure that our units cancel to give us the right thing. So let's draw parallel plates. What work is done to move that ion 1.5 times 10 to the 3 meters from its original position? So here's some parallel plates. Negative on the bottom, generally, positive on the top. You can do either. The one thing that's really key here is that this aluminum is positive. So this aluminum has a positive charge. So we have an electric field that always goes from the positive to the negative. And we also have, because this is positive, it wants to go that way, right? It wants to go that way. But the question is asking, how much work is done to move it 1.5 meters, positive 1.5 meters times 10 to the negative 1.5 times 10 to the negative 3 meters, sorry, from its original position. So the question is really asking, how much work is done to move it up? How much work is required to move it up? So let's write down all the information that we have. We have its charge. It's 4.8 times 10 to the negative 19 coulombs. We have the electric field. E is equal to 145,000. Let's just write it down as volts per meter still, because that's just what they gave it to us in. We have displacement is 1.5 times 10 to the negative 3 meters. And we are trying to find what work is done. So this is one of those scenarios where I have a whole bunch of stuff. I just go up here. I know that I'm trying to find W, so I know I'm using that one. I have Q, so I can use either of these two. I have E, and I have delta D, so I'm using these two. Very helpful. So W equals Q times E times delta D. So let's plug in all of our values, 4.8 times 10 to the negative 19 times 145,000 times 1.5 times 10 to the negative 3, which is equal to, if we plug all that into our calculators, we should get 1.04 times 10 to the negative 16 joules of work required. Okay. Now, what is the potential difference that this object experiences? So what's the delta V? So same thing, we can kind of just go through our same stuff here. We're trying to find delta V. So I could set delta V equal to QE delta D. Totally do that, right? And you could cancel out your Q's. And you could end up with delta V just equals E times delta D. Or you can, which is basically the same thing. Another way that you could do it is you could set your work equal to Q times delta V, which is the way that I just did it. Actually, in hindsight, I probably should do it like this, but either way, it will give you the exact same answer. You can try it that way. I'm going to do it this way. So work, we just calculated, is equal to Q times delta V. So delta V is equal to, I mean, just so we're all aware, right? If I'm trying to find delta V, is going to be work divided by Q. So work is 1.04 times 10 to the negative 16. And my Q is 4.8 times 10 to the negative 19. And if I do that, I should get 218 volts of potential difference. Okay, that's it for the lesson for today. You can move on to the practice problems, and you'll have tomorrow to work on these as well. So there's 5 of them. There are some that are pretty tricky, so just make sure that you're referencing the solutions manual when you need to. Okay? Don't rely on them too much at the beginning. Always try the questions on your own at first, and then if you can't get it, then you can definitely just use the solutions manual to help you get to that proper or that final answer. Okay, so have a great rest of your day, and I will talk to you all tomorrow.